Okay, good afternoon, ladies and gentlemen. This is Professor David J. De Los Reyes. What I will be discussing this afternoon, it's October 20, 2024, and the time is 5:25 p.m. My topic for this afternoon or early evening will be a continuation of my long video format topic, DC circuit. So, for those of you who are taking up electrical engineering, this is for you guys. Okay, let's proceed. The title of the subject matter for this afternoon or early evening, this will be DC circuit, lesson number 20. We are running smooth. And we are on the subject matter solution of a circuit in the computation of a current using the so-called superposition theorem. For this evening or this afternoon, I will be continuing lesson number 19 because lesson number 19 is actually an example problem, okay, by presenting the solution superposition theorem. Lesson number 19, if you would go back to my lesson number 19, comprises of 3 voltage sources which are connected in parallel, okay, connected to a 16 ohm load. And lesson number 19, I presented the solution of that one by using the so-called superposition theorem solution. And actually what came out is that this will be the answer for lesson number 19. The current passing here, I sub 16 ohm, is 1.2197 amperes. That is by using the so-called superposition theorem. So the question is, how do we know if this solution was correct or not? So to be more accurate, I will be presenting this circuit lesson number 20. I will be solving the same solution. I will fact check it. Okay, I will check the validity of the answer by using Thevenin's theorem. So it seems for this morning, this afternoon or this early evening, we are actually studying the concept of superposition and Thevenin's. Okay, because the solution for previous lesson number 19 is actually by using superposition, and what came out is this current here. The current passing here due to these 3 voltage sources here with all the circuit parameters is 1.2197 amperes. And let us try to check the validity or fact check, okay, the validity of this answer here by using Thevenin's theorem. Okay, let's proceed. So the circuit diagram of lesson number 20 will be the same as for lesson number 19. This is the circuit diagram. So we are solving the same circuit and we are checking the validity of the answer 1.2197 ampere by using Thevenin's. So for those of you who do not have yet a full grasp of Thevenin's theorem, this is for you guys. Okay, let's try to bring out the solution. Step number 1 under Thevenin's, we'll try to disconnect the load. Disconnect it. Then we'll try to compute for the voltage across this. What will be the voltage across this? Okay, we try to disconnect this one. We'll get our ammeter or voltmeter here, and we connect it here. Okay, what will be the resulting voltage that will come out? In Thevenin's theorem, we call that one ETH. ETH is capital letter E. The subscript TH refers to Thevenin's. ETH is referred to as the so-called open circuit voltage. So actually, what we could measure here is the term voltage designation ETH equal to. After the disconnection, because we will try to disconnect the load first. Okay, so this is an open terminal where get our voltmeter, what will be ETH. And theoretically speaking, how could we compute for ATH? Okay, it will be something like this. The resulting diagram will be this. We disconnect the load 16 ohms, so the configuration will be this. This is an open circuit thing. Okay, this is just a voltmeter. So to simplify the calculation of the open circuit voltage, I will try to compute first the circulating current, because if we try to disconnect the 16 ohm load with this given configuration, there will be circulating current. And I designate the circulating current on the first loop to be I1. I will consider this one as I1. And the next loop, I will consider that one as I sub 2. So for the meantime, there are only two unknowns, I1 and I2. Because to compute for ATH, we must have to compute first for the current emanating from the 24 and the 18. So we could compute for this one. So it's a must that we will compute for I1 and I2 before we could compute for ATH. And to solve for I1 and I sub 2, we will be using the so-called Kirchhoff's voltage law. So considering the I1 loop, the first loop, take the summation of the voltages and they should be equal to 0. That 24 is a voltage source, that's plus 24. Okay? Considering I sub 1, it passes through this 1 ohm and 2 ohm. So the voltage drop across the 1 ohm and 2 ohm will be the product I1 times the quantity 1 plus 2. This one here refers to 1 ohm and this 2 here refers to 2 ohm. Okay, we are considering the I1 loop. And there is an effect for this I sub 2 considering I1 loop. This I sub 2 will go against I sub 1, so this should be a voltage rise. This is voltage rise. This minus here is a voltage drop. Okay, so the sign of I sub 2 considering the I sub 2 on the next loop will be plus. Okay, multiplied by I sub 2. Minus 18, this is from plus to minus 18, and this should be equal to 0. Simplifying this one, this is just pure algebra. We'll come out with equation number 1, 3I sub 1 minus 2I sub 2, and this should be equal to 6. Considering the I2 loop, okay, we will start, we'll take again the summation of the voltage considering this I2 loop here. So this is plus 18 minus the plus is a voltage source. This is a voltage drop. This is a voltage drop due to I sub 2. So this is I sub 2 multiplied by the quantity summation 2 plus 3. This 2 here refers to the voltage drop here. And this 3 here times I sub 2 will be the voltage drop here due to I sub 2. Okay? What are the other voltage drops or voltage rise considering I2 loop? This I sub 1 here has an effect on I sub 2. So this I sub 1 is against I sub 2. So the first one, this is voltage drop. This one is voltage rise. Right. I1, the effect of I1 considering the I2 loop, it will be voltage rise because it is against the current I sub 2. So this is 2 times I sub 1 is actually the voltage drop here due, or voltage rise here due to I sub 1. So this is I sub 1 multiplied with 2. This term here is from plus to minus because this is minus to plus, this is plus to minus. So this should be voltage drop and this should be equal to 0. Again, this is just pure algebra. If we try to simplify, what comes out will be 2I1 minus 5I2 plus 6 equal to 0. Plus, this is equation number 2. I could present the solution of I sub 1 and I sub 2, but that's just pure algebra. So I just place it here. If we try to solve simultaneously equation number 1 and number 2, I sub 1 will be 3.818 amperes. I sub 1 is bigger. I sub 2 will be 2.727 amperes. So this is 3.818. And I sub 2, this is 2.727. Okay. So to compute for ATH now, we could actually present two solutions. The first solution for the computation of ATH, consider the 24 volt source here. Take the summation of the voltage here up here, because the voltage drop here is same as ATH. So we could actually present two solutions. Again, taking the summation of voltage is equal to 0. This is plus 24 minus the drop here. Okay. This is the voltage drop, the one we are looking for. This is same as ATH. This is still ATH. Right? The voltage drop here, same as this one, same as this one. So if we take the summation of the 24 volt source, 24 minus the drop here is actually ATH, because the voltage here that appears here is ATH. So 24 minus I sub 1 times 1 minus ATH, and this should be equal to 0. And if we try to simplify this one, because we are now given I1, this. If we try to subtract this one, it will be 24 minus 3.818 times 1, and this is approximately 20.18 volts. What will come out here is 20.18. And this 20.18 is same as the voltage here, same as here, same as here, same as here. So in the computation of the voltage here, we just take the voltage summation considering the 24 volt source. And that's the first solution. And as you check to the validity of the open circuit voltage, I will check the summation of the voltages considering the second law. Okay, 18 minus the drop here minus ATH should be equal to 0. So actually, there are two. 18 minus I2 times 2, but this I1 here got an effect. It should be plus I1 multiplied by 2 minus ATH, and it should be equal to 0. Since we know I sub 2, sorry for that one, and I sub 1, the only unknown now here is ATH. So as a second solution, if we try to simplify this, ATH will still be 20.18 volts. I just present the second solution so you believe in what I am solving. Okay? Step number 2. So we now know the open circuit voltage. After the disconnection, what comes out here is 20.8 volts. Step number 2. Solve for R with subscript H, meaning the open circuit resistance. Okay? We'll try to short out the first voltage source. We try to short out. Then we'll just connect, right? Okay? Then we'll get an ohmmeter. What will be RTH over here? Right? We are through with the open circuit voltage. So we short all our voltage sources, but the internal resistances should remain in the circuit. So in the computation of RTH, we will consider 1 ohm, 2 ohm, and 3 ohm. So if we try to short out the 3 voltage sources, this will be the configuration. First one is 1 ohm, 2 ohm, 3 ohm. No more 24, no more 18, no more 12, because we short it out under step number 2. And what will be RTH equal to? If we try to observe the resulting figure, these three here are in parallel. And since there are 3 resistances in parallel, if there are 2, it will just be simply the product all over the sum, the single equivalent. But since this is 3, we can do anything. It will be a summation of this so-called reciprocal. So 1 over RTH, the single equivalent, will be 1 over 1 plus 1 over 2 plus 1 over 3. There are 3, right? Okay. This is now fraction. We are solving that under algebra. If we try to compute for RTH, it should be 1 over the sum of this one, which is 1.833. and what will come out will be 0.545 ohms. So the value here is 0.545 ohms. So meaning to say, after the shorting of the voltage sources, if we try to get our ohmmeter here, what will come out will be 0.545 ohms. And step number 3, draw the Thevenin's equivalent circuit. We have solved already for the open circuit voltage by using our knowledge of the so-called Kirchhoff's voltage law. And we already have solved the open circuit resistance by using our knowledge of the concept of parallel circuit. And step number 3, we'll try to reconnect the open circuit voltage and open circuit resistance. For Thevenin's, this should be in series. So the voltage, the open circuit voltage is in series with the open circuit resistance. This is actually the original terminal. Okay, so we'll try to reconnect the load, and which the current is the one we are looking for. So we try to reconnect it. So after the reconnection, obviously RTH and the 16 ohm load are actually in series. So to compute for the current passing through the 16 ohm load, okay, since we are given a simple series circuit now, it will be the total open circuit voltage 620.18 divided by the sum of 0.545 plus 16. So 20.18 divided by 16.545. Luckily, this is 1.2197 amperes. It is same as the solution using the superposition theorem. So our solution the last time around under lesson number 19 by using the superposition, we could not check the validity, I am telling you. I will only believe that that solution is correct if we could check that solution by using another theorem. And for this evening, what comes out is 1.2197 amperes. Same as the superposition theorem solution. So our knowledge of the solution of current in a certain part of the circuit by using superposition theorem was correct. Okay. Good evening from Los Angeles. This is Professor Navigator.